Hey everyone, welcome back. Today we're going to take a look at vertex shaders in TouchDesigner. This tutorial is meant to be an introduction to vertex shaders and a way to start to understand some of the concepts and practical applications of vertex shaders so that you can better understand when they fit within your workflow and when you can save yourself a ton of time by doing something that's pretty simple in vertex shaders that's maybe not so simple in Sopland or using just fragment shaders or whatever else. So our our code is not going to get too complicated. It's actually going to be relatively light, and the purpose of this tutorial again is going to be kind of getting the whole thing set up, understanding where we're getting the variables that we're working with, and then manipulating some vertices with our vertex shader to result in what we're looking at here, which is just a nice field of waving lines that I find very attractive. So, as normal, I will just get rid of all of this, but before I do, I'll jump in and show you that there's really not that much going on in here. There's just a little bit of input, a custom GLSL material, that'll be most of the heavy lifting, and then just a little bit of rendering and post. So, I'll delete all of this, and we can get started. So first, I'm going to just make myself a component, and I'm going to call it waving lines. I'll jump inside this component, and I'm going to drop down a line sop. From there, I'm going to drop down a geo. And here, I'm just going to complete the rest of my render network. So I'll grab a camera. I'm going to do an ambient light right now. And then I'll do a render and use Alt-N to drop down a null, which I'll name backgrounds, and then we'll background that top. The last thing I'm going to do right now is a Fong, and I'll just drag and drop that Fong onto my shader. And now we at least have something that we can look at. I guess I'll put a transform down too. And make it just not black. Okay. So what is a vertex shader? I'm going to link a video in the description that actually does a much better job than I would do at explaining what a vertex shader is and kind of how it fits into the rasterization pipeline. But for my purposes, for our purposes, it's easiest to think about the vertex shader as a program that we're going to run over, a program that we're going to run almost like a for loop over every one of our vertices in our geometry. So this line right now, because it has 2 points, has 2 vertices. And so a vertex shader would operate on both of those vertices in parallel by executing the same code, that is, whatever is in our shader. That probably sounds somewhat familiar because it's the exact same paradigm the fragment shader works in. Specifically, it executes a block of code, the fragment shader, on every fragment or pixel of our screen in parallel. That is what makes the GPU so fast at performing so many calculations, and it's that same speed that we want to leverage here using our vertex shader. So you can think of the input to the vertex shader as an array of vertices coming out of our geometry, coming out of our SOPs. And then the vertex shader code will be called over every instance in that vertex array every time the shader is invoked. To actually get our shader, we can click on this Fong and just press Output Shader here. We don't need any of this, we can just press OK. We can then delete our original material and drag and drop this new Fong GLSL material. I'm not going to use this pixel shader, so I'm just going to dock that, and then we have our vertex shader and our info. And this is a setup that I think everybody should be pretty familiar with from working with GLSL tops. So I will edit this vertex shader, and first we can just take a look around the code and start to understand what we're working with. So here we have our vertex shader code. We can see our uniforms up here at the top as normal in our fragment shader. Then we have this block here, which is known as a struct. It's just a way to package data together in GLSL. The name of the structure is vertex, so you can think of that as like a class. And then over it would be the specific name of the instance of our class that we're working with in this invocation of the shader. Down here in our main function, which is obviously what's called on every vertex in our vertex array, we have a lot of these TD functions. And these are functions that TouchDesigner has defined for us that will help us just kind of work inside of the vertex shader a little bit easier. So they're basically just helpers that TouchDesigner has defined for us. You can learn about those here on the TouchDesigner documentation. This page is called Write a GLSL Material. I highly recommend everybody read it several times, probably, but at least once as you're going through this. So here it kind of goes through generally what the vertex shader is and what the pixel shader is. So here it says, you have access only to one vertex, which we already know. The input to a vertex shader is all the data about a particular vertex the program is running on. Data like this vertex space, or position in SOP space, texture coordinates, colors, and normals. These variables are called attributes. Attributes are declared using the in keyword. We'll come back to that in just a second. And then the output can also be many things, as it says here. So we're going to be outputting vertex position, but we can also output things like color and texture coordinates, which can then be used in the fragment shader. And then, as it says here, outputs from the vertex shader are interpolated linearly across the surface of a primitive the vertex is a part of. So that is how the fragment shader will then determine what color pixels are. The surface, the primitive the vertex is a part of, will generally be quads or triangles, and then it'll take the color of the vertex at each of the three corners of the triangle and then interpolate those colors across the face, and that's how we get a nice gradient in our color renders. Now, if we scroll down to working with geometry attributes, it tells us that some attributes have been declared for us to use in our vertex shader. So these are things like the vertex position, the vertex normal, and the texture coordinate, of which there is an array with 8 layers, or 9 layers. So what this means is that we can use the variables P, N, and UV just in our shader without declaring them. So whenever you see this capital P, such as here, when I first came across this, it took me a really long time to figure out, like, where's P coming from? You can't just use variables in code without declaring them, like, what the hell's going on here? This is the answer, although it took a while to figure out. So here, these pre-declared attributes are going to be important to use because we're basically going to use these as the basis and then deform these attributes in our vertex shader to position our geometry where we want. So the last thing I'll say about these attributes is that they are coming from our SOPs. So if we insert a point SOP, we can see that the positions here, this corresponds to your position attribute. And so if we were to move or add 1 to the X position attributes for all of our points, then we can see that it moves here. And we could then, I guess, like undo that transformation by defining a vec3 called new position and setting that equal to p, setting it equal to p, and then saying new p dot x minus equals 1, and this will undo our point sop transform. And then we can just deform with our new p instead of our old p, and then when I allow it to render, our point moves back. So basically, this operation and this operation are inverses of each other. So here we're doing the exact same thing, i.e. adding 1 to the x attribute of our position, and here we're subtracting 1. So this shows that you can accomplish the same thing in SOPs or the vertex shader, but this SOP is going to be using our CPU, and it's fine if you have 1 line and 2 points, but if you have a couple hundred lines and a couple hundred points, then even something like just simple transformations can get rather unruly if you want to start animating those transformations in a SOP context. So the real power of the vertex shader is that we will be able to do a ton of this geometry deformation in the GPU and directly in the rendering pipeline, which will save us a ton of power. So from here, we can start to think about how we can actually get all of our lines to manipulate. And then basically what we'll do is just add some code here to manipulate all our lines. And then that's really it. And we'll see that it's actually a pretty simple process. So first things first, we have to get some more lines. I'm going to maximize this. I'm going to customize my component and add a couple parameters before we get going. So resolution, of course, need to add that. I'll add the number of points on our line, which I'm going to reference. Bind. I'm going to add a variable called bounds. That'll be an XY. And I'm just going to make this minus 10 to 10. And then I'm going to use these bounds to set the X and Y positions for my line. Now we can move our camera and start to see the line across our whole screen. That's good. Now I'm going to go on to instancing. I'm going to turn on instancing. I'm going to make it a manual instance count. Drag and drop this number of instances over here, and then I'll make it 50. And of course, I wanted to bind this. Make it 50, and then I'm going to give myself many more lines. So I'll make this max 1,000. So now we have a bunch of instances. We have 50 instances, but we're not seeing them here. And that's because nothing is happening, or we're not moving our instances at all. So if we go back to our documentation and we Control F for instance, we'll see that vertex shader only functions includes a function named td instance id. And this td instance id will return an integer that will be the ID of our instance. And so I'm just going to create a new variable called ID. and set it equal to the output of this function. So this will be 0 for our first instance, 1 for our second instance, etc. So what we can do to visualize this is say new p dot x, or maybe dot y, plus equals id. And if we do like id times 0.1, then we can see that all of these instances, now all 50 of them, are nicely arranged, and each of them are just translated 0.1 above the last. Now, the issue here is that as we reduce or add instances, we grow. And it kind of just like is an ever-growing stack. I don't really want it to be an ever-growing stack because then I have to reposition my camera. I don't want to do that. So what I really want is to have all of these instances positioned very nicely within the same space so that as I add more, they become more densely packed. You can actually do that pretty easily using a GLSL top. And what we'll do here is just create a texture that will have 0 at the bottom and 1 at the top, and a linear interpolation across going up the texture. 1 pixel for each of our instances, and then we'll just use the handy translate op functionality in the instancing to be able to actually position our lines. So I'm going to call this UV. I'm going to drop this on our translate, and I'm going to translate my Y with the G. Now I'm going to get rid of this for now, so we're back to having no translation at all showing, but we'll get that back in just a second. In my GLSL, it's actually going to be super simple. You probably already guessed this. We're just going to take vuv.st for our RNG values, 0 for our green, sorry, for our blue. And then all we need to do is set the resolution to be 1 pixel wide. And, oops, where are my parameters? And then the number of instances will be the number of pixels tall. If we want to, we can scale this. Whoops, we need to make it a 32-bit float. But if we make it 32 bits, then we can scale this so that we can cover the range, or change the range that our instances are going to fill. But then, because this is going to be consistently linearly interpolated and rearranged, no matter how many pixels there are, it's always going to be from 0 to 1, or from 0 to whatever our multiple is. This means that when we add and subtract instances, the screen space taken up by these instances is constant, and only the density changes. And that is exactly what we're looking for. So that's great, because we now have a consistent screen space where we can add and take away the density of these things, which translates very well to allowing us to use a texture like a noise, which I will turn off monochrome and make 32-bit float, using a texture like a noise as a turbulence to actually deform these instances. And that is what we're about to do in our vertex shader. So before we start working in the vertex shader, I'm going to add some uniforms. These are added just like uniforms in our normal GLSL shaders, GLSL top shaders. So the first one is going to be U bounds. That one I'm going to drag and drop my bounds parameter to, and just the X and Y. Then we're going to want U num lines, and this is going to be our number of instances, which I want to rename to number of lines, just for clarity. So those are the two that we'll need right now, as well as uTime, and this will just be abs time dot seconds. And then we declare additional additional uniforms in the form of samplers. These samplers are textures that we look up. So essentially, when you wire a top into a GLSL top, what TouchDesigner does for you under the hood is declare a texture sampler or a uniform sampler using that texture input. And so we're just doing that here manually because it's the Vertex shader, so we don't have that nice like TouchDesigner under the hood functionality to help us out. But it's pretty easy to do this, so we can declare a sampler. I like to start them with S. I'm going to call this S-turb. And my top will just be turb, this noise. I'm going to make this noise period a little bit bigger for now. Okay, so now we have a bunch of our uniforms declared now. We can start to get into the Vertex shader and declare the uniforms here before we use them. So I will have a uniform float uTime. I'll have a uniform vec2 uBounds, and then I'll have a uniform float uNumLines. So what we're going to do is use a little bit of math to map our vertices from world space, which is where they are now, to screen space. And then we're going to use those screen space coordinates for our vertices to look up a turbulence value in our turbulence texture and then deform the vertex based on that turbulence. This is, again, very similar to what TouchDesigner does under the hood when you use deform vertices, displaced vertices rather, in a Phong with a height map. Pretty similar overall process, but here we're doing it with our own custom stuff so that you can see how to use this a little bit more, particularly for your use cases. So we'll need a helper function to do this because what we're going to do is take our instance ID, which we know goes from 0 to the number of instances we have, which is the same as number of lines. We're going to define a function called map that's going to just return an interpolated value. It's very similar to map and processing or TDU remap or rearranging with a math top. And then all we'll need to do is grab our current instance ID, normalize that between 0 and our number of lines, and that will give us our normalized Y value, which we can use to then look up the row of pixels. And then we can look up the column of pixels by using the actual X location of the vertex, because we don't know the vertex number. So we can't just say, okay, there's X vertices, I'm vertex 50 of 100, so that I know I'm exactly in the middle. We don't know what the vertex number is here, so we can use the vertex position and normalize that vertex position between our bounds, which is why we're intaking our bounds. So first we can define a function called map. That function will return a float, and we'll take in 3 floats. Or sorry, it will take in 5. There will be float x, and then float a and b, which will be our in range, and then float c and d, which will be our out range. So x is value to map, AB is input range, CD is output range. And then our function will return C plus X minus A over B minus A times D minus C. This is a very, very standard remapping function, and then if you want to, you can also clamp this value between C and D so that the output is always going to be within this desired output range. Basically, what's happening here is you calculate here the percentage of the range A to B that X falls upon. So that's taking this X minus A is like how far is X from the beginning of the range divided by the entirety of the range. So this gives you a normalized percentage of what X represents in this range. And then we multiply that by the size of the output range, and then just add that to the beginning of the output range to rescale it. So that's what's going on here, and we're going to use this function to create a new variable called UV, and that is going to be a vec2. And the x component of that vec2 is going to be using p.x, and it'll be remapping p.x from our ubounds.x, ubounds.y to 0 and 1. And then our y value of this UV lookup will be mapping our instance ID from 0 to unum lines to the range 0 to 1. And so this allows us to calculate normalized screen space, or really texture space chords to use in lookups. So again, very simply what we just did there was look at the position of the vertex, and that position is in world space. So that position falls somewhere between negative 10x and positive 10x. So we take what that x value is, and then we map it from negative 10 to positive 10 to 0, 1. And then similarly, we map the ID, which is from 0 to 50. We remap it from 0 to 50 to 0 to 1. And so the output is going to be vec2 from 0 to 1 that we can use to look up our textures over here in our turbulence. So we can visualize this really quickly by declaring a variable color that is a vec4 and setting that vec4 equal to our UV, 0 for blue and 1 for alpha, and then we can just override this TD point color down here with our variable color, and now we can see that our vertices are all being colored very nicely with this UV pattern, which I'm sure you know, but I will illustrate anyway. Looks very similar to our classic UV pattern in the GLSL top. So that gives us some confidence that our remapping is working correctly. And if yours doesn't look like this, then you should check out your remap function here, as well as making sure that all of the variables are appropriately linked to uniforms. So what do we do with this information now that we have it? Use UV chord to look up turbulence text. So vec3 turb equals texture, and here we're going to use our sampler sturb and UV, and then just take the RGB values because we have a vec3. We're getting an error. Sturb is an undeclared identifier. That's because I forgot to declare it up here in my shader. So we declare that in the shader with uniform. The type is a sampler 2D, and then I call it sturb because that is what I called it here in my shader samplers. we can take a look at our turbulence texture by replacing the first three components of color with it. And this is looking decent. Maybe if we animate our noise a little bit, we can see what's going on a bit more. So average time seconds times 0.02. Cool. And we can start to see that this is indeed working, although it's obviously stretched because our aspect ratios are a bit funky, given that these lines are so long and skinny. It doesn't really matter, but you can obviously change the aspect ratio if you want so that it's not distorted. So now, instead of doing this just like arbitrary new p dot x minus equals 1, what if we just say new p plus equals turb? And now we can start to see that our lines are indeed animating, but it looks very clunky. And this is actually also the reason that our texture was so distorted, so I apologize. The reason for this is because we only have 2 points. And so there's nothing to distort. You can't have a bendy line with only 2 points. So let's give ourselves a lot more points than that. Maybe like 200 points. And then we can also make the offset 0, which means that we lose some color. So maybe we want to define a separate sampler for our color. So I will define a separate noise, and I'll give myself a ramp. I want to make the ramp something. I make whatever you want. I just want to make it some colors that are interesting to me. So I'll make this like a darker purple. Maybe over here, this red will be a bit of a darker, like burnt orange, and then this red I think is a darker purple too. Something like that is pretty nice. And then what I'm gonna do is use a remap. This noise I'll make 8-bit. Flip these components around, turn the extend to repeat, and now we have a nice little texture that is colorized by our noise. You know, I actually don't think I want that 8-bit. I definitely want it 32-bit. Yes, okay, and so now we have a nicely remapped colorized texture that we can use. And so I'll name this color and add another sampler called scolor, which I will also add to my shader. And then we can colorize by simply copy and pasting here and replacing this with scolor. Here we have an error. We don't need just the RGB. We can take all 4 channels. And so there you have it. Now we have a bit more colorization going, and obviously this can all be changed to be can be changed to be whatever you want. Maybe this should be like a little brighter, whatever, it doesn't really matter. We're gonna update that color from a palette in a little bit anyway. So for right now, it's just so that we can actually see what we're working with. Yeah, and so now we're already starting to see the power of what's happening here. I'm gonna up my resolution here to 4K, and I'm also going to customize my component. Go over here to my common page, turn on wireframe to topology wireframe, and then parameterize this line width. And what that'll do is let us increase or decrease the width of these lines, which just helps our visualization. So at this point, we have the basis of this effect pretty much set up and working. We have a sampler that's using a texture to deform our instances. The instances are being deformed, in this case, X, Y, and Z, so maybe we actually don't want that. Maybe we just say new p dot z is equal to our turbulence. And then this will keep our X and Y positions fixed. So we kind of retain this like grid-based look. And we see what's going on if we start to turn our camera with some like perspective. So now we can start to see this rippling a little bit more, which I like a lot. And yeah, I mean, this is pretty much the effect now. So from here, we can go to just finalizing things and getting it ready for your next steps. So one thing that I like to do is parameterize this noise period. Maybe we make that period a maximum of like 5. I think that could be interesting. And then we wanted to give it a minimum of like 1. I don't really like playing with the harmonics so much because it gets pretty busy pretty quick, and you can't really like switch them without it jumping. But you can pick the level of harmonics that you like and stick with that. I think I'm going to stick with maybe 2. Spread I'm going to leave it 2, but the gain I am going to take. I like the gain because it's a nice smooth transition. So that's good. Amplitude is probably another good one, and maybe even exponent, because that's kind of cool, especially with like a lower amplitude. Yeah, that could be interesting. So sure, we can drag and drop our exponent and our amplitude. We have our line width already. Yeah, so let's take a look at where we're at, I guess. Let's see. Come up here. Okay, so we can give ourselves fewer or more instances, which is great. You'll notice even at like 1,000 instances, or I don't know, probably even at like 10,000 instances, 50,000 instances. Okay, maybe not. I think there's actually an issue with that, but 30,000 should be fine. We can go up to 30,000 instances, no problem, doing all of this real-time deformation. And that would be pretty difficult with just using SOPs. Obviously, we don't really need that many right now, so I'll go back down, play with the line width. Oh, actually, one thing that we should definitely do is go into our material, turn on blending, leave it as add, and then if you go here, we can change this alpha front to decrease the alpha of each of our vertices. So this will let us have it be like brighter where there's more overlapping. This weird like flickering stuff we can fix by turning off the depth test. And what that means is that it doesn't toss out vertices that are behind other vertices. Because these are moving and turbulent, when that's on, it results in the flickering because what's in front is always changing. So if we turn that off and then go play with our texture again, or sorry, our alpha again, now we kind of have this cool, brighter in some spots, darker in some spots. I don't know, almost more of like a membrane type look. So perhaps alpha is a float that we want in here, and then we can just use Python. And we can default it to 0.5. So yeah, that gives us some additional ability, especially if we have like a lot of lines and we make the alpha smaller. So there's a lot that you can play with, just kind of to get the different visual effects that you're looking for. But obviously, we can also just max it out, and you have more of this spatialized, spatialized look here. A couple other things that you could do would be to use a light and not an ambient light, and then this will let you kind of just play around and tweak, and you can maybe use multiple lights to just have highlights that are more variable than just that ambient light. So for example, maybe there's one light that I put there, and then this other light I'm going to put underneath and maybe like change the perspective of and put this way. The idea being that only some of the lines then, only in some locations, will kind of get the highlight from this extra light. And you could even animate it if you wanted to, although I'm not going to do that right now. And then one other thing that's pretty helpful is just using this camera blend operator. So you just wire both of these cams into the cam blend and then drop it on the render as the camera. You can change it to sequence, and then if I move camera 2, like let's say it's just the straight on front view, maybe like zoomed in a little more, you can then use this sequence parameter to actually blend between your two camera views super easily, which can help or just provide fun animation. So for example, like, I don't know, it could be a very different view, and we can see that we can then transition, although this transition doesn't look super nice, but it allows us to play with different views in a little bit more easy to switch around way. So I kind of like these like disappearing into the distance perspectives like this. So maybe I'll leave that as my second camera, and then I will parameterize the sequence. Now, there's obviously all sorts of posts that you can do. I'm going to, I think, leave that as an exercise for the viewers, because this is really where I wanted to end this tutorial. I think it's a very good way to explore using the Vertex shader. This is something that would be somewhat difficult to do outside of the Vertex shader, but as you can see, we're using very few operators, and this was, yeah, not too hard of a process to replicate. So I did mention we'd be using palettes, so I guess right before we end, I will add palette. I use this Color Lovers picker that you can grab on the forum. It's actually super simple using this remap. We can just wire it in to replace our ramp. And then, boom, we have a palette. I'll actually make it an input. Call it in color. And then I suppose I'll make an input for our turbulence and call that in turb. Then our color, we can take up to our top level and wire that in. And then our turbulence I'll just leave here. And so now we will have this component that should be very transferable and give quite a bit of functionality. We're able to switch our camera views, add tons more instances, take down the alpha. I mean, this is already looking really nice. Play with the harmonic gain, the exponent, and yeah, just change a lot of things about our system. How do I get all of this back? Exponent 1, harmonic gain 0.7. Our noise period we can play with. And yeah, you can add yourself more points or less points. As you do fewer and fewer points, it'll become obviously jumpier. But yeah, hopefully this has been a good overview, good intro to Vertex shaders. Hopefully it inspires people to keep using Vertex shaders more in the future projects. And I will close by saying thank you to all of my Patreon supporters. It's been truly a life-changing experience for me so far, and I can't thank anybody enough for all the support and frankly some of the confidence too. So I appreciate all of that so much. And yeah, until next time, hope everyone enjoyed.